For 50 years, the best computers on Earth tried to blow up a star. Every single simulation failed. The shockwave stalled, the core sat there and nothing exploded. Meanwhile, real stars were detonating across the sky every week. Scientists could watch the explosions. They just could not make one happen inside a machine. And the reason kept pointing to something worse. Some of those stars were never exploding at all. The official explanation is clean. A massive star burns through fuel. The core collapses, the collapse bounces, and the star explodes. Simple. Except the most massive stars skip that last step. Above a certain weight, the core caves in and nothing comes back out. Almost no light escapes. The star dims to a faint red glow and then vanishes. That should be easy to confirm. Point a telescope at a heavy star, wait, and watch the star disappear. A team did exactly that, monitoring 231 galaxies over 10 years. The result, 0 confirmed vanishings, not one. Either the silent deaths are far rarer than the models predict, or the signal is so faint that no instrument on Earth can catch the glow. And the predictions themselves rest on a single number, a nuclear reaction rate measured in a lab that nobody has nailed down. Shift that measurement by the margin of current uncertainty, and a star 10,000 light-years away switches from spectacular explosion to silent disappearance. The question is not how stars die. The question is whether the universe hides the most violent events in total darkness, and whether we have been looking at the wrong evidence for half a century. This video is one entry in a much larger series. If you want to see where the rest goes, hit that like button and subscribe so you do not miss what comes next in this story. Stars explode. That much is obvious. Astronomers have watched massive stars detonate for centuries, briefly outshining entire galaxies before fading into debris. The mechanism should be simple. A dying star exhausts nuclear fuel. Gravity crushes the core rebounds, and the rebound rips the star to pieces. Clean, elegant. And for more than 50 years, every computer on Earth has tried to make that sequence happen. Every single attempt failed. That is the part nobody talks about. Real explosions happen in the sky every week. Telescopes catch the light, instruments measure the blast energy, and the data confirms what everyone already believes. Massive stars die in violent, spectacular fashion. But when scientists sit down and try to recreate that violence inside a machine, the math chokes. The shockwave stalls. The core just sits there. Nothing explodes. The most basic explanation for how stars die has been broken at the most fundamental level since the 1960s. For decades, nobody could figure out why. The official version of the story goes like the following. A star more than about 8 times as massive as our sun spends millions of years fusing lighter elements into heavier ones. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen, neon, silicon, and finally iron. Iron is the dead end. Fusing iron does not release energy. Fusing iron consumes energy. So when the core of a dying star fills with iron, the engine that held the star up for millions of years simply stops. Gravity wins. In less than a second, the inner core collapses from a region the size of the Earth down to a ball roughly 20 kilometers across. The density of that ball exceeds the density of an atomic nucleus. A single teaspoon of the material would weigh more than 1 billion tons. That collapse is violent enough to create temperatures exceeding 100 billion degrees. And at those densities, the collapsing material slams into the newly formed core and rebounds. A pressure wave races outward through the star. That pulse should be the explosion. That pulse should rip the star apart and scatter heavy elements across the cosmos. But the blast does not do that. The blast stalls. Within milliseconds of launch, the outgoing wave runs into the rest of the star, still falling inward. The infalling material is dense, heavy, and moving fast. The blast plows into that wall and loses energy. At the same time, the extreme heat at the shock front starts ripping heavy nuclei apart, breaking them into individual protons and neutrons. Splitting those nuclei costs enormous energy, and that energy comes directly from the blast wave. A flood of particles called neutrinos streams outward from the newly compressed core, and those neutrinos carry away still more energy. The numbers are staggering. In the first second after bounce, the core radiates more energy in neutrinos alone than the sun will produce in 10 billion years of steady burning. Almost all of that energy escapes into space, doing nothing useful for the explosion. Within a fraction of a second, the blast has bled so much energy that the wave simply dies. The front hangs in space, at a radius of roughly 100 to 200 kilometers from the center, neither advancing nor retreating. Accretion continues. Material keeps piling on, and the explosion that should have happened just sits there, suffocating under the weight of the star that was supposed to be dying. Sterling Colgate and Richard White, working at the Los Alamos National Laboratory, were among the first to put the problem into a computer. The year was 1966. Simple by modern standards, the model was perfectly spherical, treating the collapse as if the star were a smooth, uniform ball imploding evenly in all directions. Every researcher expected the result to confirm what everyone already assumed. Instead, the shockwave launched, stalled, and died. Colgate and White published the result and moved on, confident that better calculations would fix the problem. Better calculations did not fix the problem. Through the 1970s, the 80s, and the 90s, groups at dozens of institutions around the world tried variations of the same approach. More physics, better equations of state for nuclear matter, improved treatments of neutrino transport, faster computers. Every answer was the same. The shock wave stalls. Nothing explodes. Every run ended the same way, with a dead shock wave hanging in the interior of a collapsing star, going nowhere. The frustration in the field was extraordinary. Astronomers were detecting roughly one core collapse, supernova per century, in a galaxy the size of the Milky Way. Across the observable universe, that translates to roughly one supernova per second. The explosions were real. Debris was real. Heavy elements forged in those explosions were real, spread across the cosmos, built into planets, built into the bones and blood of every person alive. Every telescope, every spectrum, every debris field demanded that massive stars explode. Every equation, every simulation, every model said the mechanism was broken. Graduate students entered the field in the 1970s, spent entire careers wrestling with the problem, and retired in the 2000s without seeing a clean solution. Professors who had supervised the first doctoral theses on core collapse watched their own students inherit the same unsolved puzzle. The question that should have taken a decade consumed generations, and the deeper the community dug, the worse the problem looked. Every improvement in the physics, every refinement in the numerical methods seemed to make the blast stall even more convincingly. I want to be clear about how strange this situation was. Imagine designing a bridge. Bridges exist. Bridges work. People drive across bridges every day. But every time an engineer sits down and runs the structural calculations from scratch, the bridge collapses on paper. Every calculation says bridges cannot stand. And yet, bridges stand. That contradiction is what the supernova problem felt like for half a century. The universe was producing explosions that lit up galaxies, and the best physics in the world could not reproduce a single one inside a machine. A partial breakthrough, when one finally arrived, came from an unexpected direction. Not missing physics, missing dimensions. Every simulation from Colgate and White onward had forced the explosion to be perfectly spherical, expanding equally in all directions like a balloon. That simplification made the mathematics tractable, but that same shortcut made the mathematics wrong. Real stellar cores are not smooth, uniform spheres. Real stellar cores are chaotic, turbulent, asymmetric environments where material sloshes, churns, and convects in 3 dimensions. Turbulence matters. Chaos matters. Every asymmetry matters. When research groups finally had enough computing power to run models in 2 dimensions, and later in 3 dimensions, allowing the collapse to be messy and asymmetric, some of the simulated stars began to explode. Not all of them. Not reliably. But some. Adam Burrows at Princeton spent decades chasing that 3-dimensional solution, working with collaborators including David Vartanian, Burroughs ran progressively more sophisticated simulations using a code called Fornax, one of the most advanced supernova simulation tools ever built. The early runs, constrained to 2 dimensions, showed encouraging signs. Turbulent plumes of neutrino-heated material pushed outward against the stalled shockwave, creating bulges and asymmetries that helped revive the blast. But 2-dimensional models imposed an artificial symmetry axis, forcing the turbulence into patterns that real physics does not respect. When the group finally unlocked full 3-dimensional capability, allowing the collapse to unfold without any artificial symmetry constraints, the picture sharpened dramatically. Neutrino heating behind the stalled shockwave, amplified by turbulent convection and the breaking of spherical symmetry, could restart the explosion. The mechanism had a name: the delayed neutrino-driven mechanism. Neutrinos streaming from the compressed core deposit a small fraction of their colossal energy into the material behind the stalled shock. That heating builds until the thermal pressure overwhelms the infalling debris and the explosion relaunches. Only a tiny fraction of the neutrino energy needs to be absorbed, roughly 5%. But that 5% carries the force of 10 billion nuclear weapons detonating simultaneously, focused inward on a region smaller than a city. But elegant does not mean solved. The neutrino mechanism works in some simulations and fails in others. The outcome depends on the structure of the star before collapse, on nuclear physics parameters measured with significant uncertainties in laboratories on Earth, and on computational choices that different research groups handle differently. A star that explodes in one simulation may collapse quietly in another, depending on which nuclear equation of state the researchers chose, which neutrino transport approximation the code uses, and how long the simulation runs before the researchers stop the clock. Evan O'Connor and Christian Ott at Caltech ran hundreds of collapse calculations. The scope was enormous, spanning a vast library of progenitor stars and several competing nuclear physics frameworks. The results revealed a patchwork of outcomes that was anything but clean. Some stars exploded easily, others refused. The dividing line depended on a single parameter, the compactness of the stellar core at the moment of bounce, and that compactness was itself a product of the entire evolutionary history of the star. Alter the mass, shift the metallicity, adjust the nuclear reaction rates, and the outcome flips entirely. And that last detail, how long the simulation runs, would turn out to be the most dangerous variable of all, because the field had a habit of stopping simulations too early. Researchers would watch the shockwave revive, see material blasting outward, and declare victory. A successful explosion, a neutron star left behind, paper published, celebration. But what happens if you keep the camera rolling? What happens if the calculation runs not for 1 second of stellar time, but for 1 minute, 1 hour, 1 day? The consequences of that habit would not become clear for years. And when the consequences finally arrived, the answer would shake the confidence of the entire field. The simulations still stall. A mechanism that everyone assumed was simple has consumed more than half a century of effort. Answers remain conditional, partial, dependent on choices that nobody has fully justified. That same frustration Colgate and White felt in 1966 has not gone away. Only the shape of the frustration has changed. But the real surprise was never that the explosions were hard to reproduce. The real surprise was far stranger, far more unsettling. Some of the biggest stars in the universe might not be exploding at all. Bigger stars die louder. That is the rule everyone carries in their heads. A star 10 times the mass of our sun should produce a death, 10 times more violent, 40 times. The explosion should be visible from the edge of the observable universe. More mass, more fuel, more gravity, more everything. That logic is the kind of logic that feels bulletproof. And the logic is completely wrong. The reality runs backward. Stars in the range of roughly 10 to 25 solar masses can explode spectacularly. The neutrino mechanism, broken as the neutrino mechanism is, manages to revive the shockwave in enough of those cases to produce the supernovae astronomers have photographed for centuries. Those are the explosions that scatter iron and oxygen and calcium across the galaxy. Those are the deaths that build planets. But climb higher on the mass ladder, past 30 solar masses, past 40, and the physics changes. The core becomes so dense, so tightly packed, that when gravity finally wins, nothing can fight back. Nothing at all. Even the neutrino mechanism that barely works for lighter stars has no chance here. Infalling material is too heavy, too fast, too relentless, and the shockwave never revives. No light escapes the collapse, and no debris flies outward. The star does not explode. The star, one of the largest objects in the galaxy, simply stops existing. Physicists have a name for this outcome: a failed supernova. Some researchers prefer a more honest, more descriptive term: an unnova. The star that does not nova. The death that produces no visible event. One moment, a red supergiant sits in the sky, massive and luminous. The next moment, the supergiant is gone. No flash. Not a single expanding shell of gas, and zero remnants glowing in X-rays. Just darkness where a star used to be. The most massive deaths in the universe are also the quietest. And that inversion, that violation of every intuition about how size relates to violence, sat buried in the equations for years before anyone realized the implications were real. Think about what that means for the entire record of the cosmos. If the most massive stars vanish without a trace, then the universe has been destroying the most massive objects in existence and leaving no receipt. No explosion for a telescope to detect, not a debris field for a spectrograph to analyze, zero afterglow, and no remnant that screams for attention, just a hole in the sky where a giant used to be. Every catalogue of stellar deaths is missing the heaviest entries, and nobody noticed because nothing was left to notice. The question buried inside that absence is whether the universe owes anyone a visible record of the most consequential events, or whether the biggest transformations can happen in total darkness with no witness and no evidence left behind. Evan O'Connor and Christian Ott, working at Caltech, were among the first to map the boundary. Using over 100 stellar models and multiple nuclear equations of state, O'Connor and Ott ran more than 700 collapse calculations using a general relativistic simulation code called GR1D. The results drew a picture that nobody wanted to see. Whether a star explodes or collapses silently depends, to first order, on a single parameter: the compactness of the stellar core at the moment of bounce. Higher compactness means the material is packed more tightly, and tightly packed cores are harder to blow apart. The relationship is not perfectly clean. Chaotic variations in each star's internal structure create pockets, places where a slightly more massive star explodes, while a slightly less massive neighbor collapses in silence. Researchers later named these pockets islands of explodability. Not a dividing line, a mosaic of fates scattered across the mass spectrum. But the broad trend held. Go heavy enough, and the star goes dark. O'Connor and Ott estimated that between 10 and 25% of all massive stars at solar metallicity end up forming black holes rather than leaving behind neutron stars. And at lower metallicities, where stars lose less material to winds during their lifetimes and collapse with heavier cores, the fraction climbs even higher. That prediction created a test. If the heaviest stars truly collapse without exploding, then astronomers should be able to check the record. Every time a supernova goes off in a nearby galaxy, researchers can look at archival images of the same patch of sky taken before the explosion and identify the star that died. Match the brightness and color of that pre-explosion star to evolutionary models, and the mass of the progenitor drops out. Decades of this forensic work produced a catalog of identified supernova progenitors, and the catalog had a hole. Stephen Smart, working at Queen's University Belfast, assembled the most comprehensive analysis of supernova progenitor identifications. The data showed a clear pattern. Type 2, P supernovae, the most common flavor of core collapse explosion, came from red supergiants. The progenitor masses clustered between 8 and 17 solar masses. Above 17 solar masses, the record went blank. No confirmed progenitor of a standard core collapse supernova, not one, had ever been found above that cutoff. SMART gave the absence a name: the red supergiant problem. Massive red supergiants exist in large numbers. Astronomers can point telescopes at nearby galaxies and count these massive stars. The population is real. But when those galaxies produce supernovae, the explosions never come from the heaviest members of the population. The giants are dying, but not a single one of those giants is producing a visible explosion. Where are the giants going? The most direct way to answer that question is to watch. Pick a galaxy. Photograph every corner of the galaxy every few months and catalog every luminous star inside the field of view. Wait. If one of those stars disappears without an accompanying supernova, that disappearance is a candidate for a failed supernova. A star that collapsed into a black hole and left no visible trace. The experiment sounds simple. The execution is brutal. Monitoring millions of individual stars across dozens of galaxies, year after year, searching for the one object that quietly winks out. Christopher Kochenik at Ohio State University designed exactly that experiment. Using the Large Binocular Telescope in Arizona, the survey monitored millions of luminous stars across dozens of nearby galaxies, checking repeatedly for any star that simply vanished. In 2009, the survey found a candidate, a red supergiant in the galaxy, NGC 6946, sitting roughly 22 million light-years from Earth. The star was luminous, roughly 25 times the mass of our Sun, and the star was behaving strangely. Between 2009 and 2015, the star briefly brightened, then faded. Not the dramatic brightening of a supernova, a faint pulse, a gentle pulse of luminosity followed by a slow dimming. By 2015, the star had dropped below the detection limits of every instrument pointed at the location. Follow-up observations with the Hubble Space Telescope and the Spitzer Space Telescope confirmed the disappearance. The star was gone. No supernova had been reported at that position, and no expanding debris field appeared in subsequent imaging. The object received the designation NGC 6946 H1, the first serious candidate for a star that had collapsed directly into a black hole. No explosion, no wreckage left behind for anyone to study, just a vanishing. Buried in the data, one detail stands out from the rest of the record. Brightness measurements of the vanishing star did not come only from billion-dollar orbital observatories. Some of the photometric data, the careful tracking of how the star changed over time, came from Ron Arbour, an amateur astronomer working from a backyard observatory in the United Kingdom. Arbour had been monitoring galaxies for decades, patiently recording brightness values, with equipment that cost a fraction of what a single night on Hubble costs. And the data held up. Those measurements sit alongside observations from the most powerful space telescopes ever built, in the same published record, supporting the same conclusion. A retired engineer with a telescope in a garden shed contributed to one of the most significant black hole formation discoveries in modern astrophysics. The universe does not care about credentials. The universe cares about who is watching. But here is the problem with NGC 6946 BH1. The star vanished. The behavior is consistent with a failed supernova. But consistent with is not proven. Maybe the star is hiding behind dust. Maybe some other exotic process mimics the signature of a collapse. No telescope, not Hubble, not Spitzer, not any ground-based observatory has confirmed a black hole at that position. An infrared signal, the kind a newly formed black hole accreting leftover material might produce, has not been detected. The strongest candidate for a star silently becoming a black hole is still, after more than a decade of follow-up, only a candidate. And the universe was about to prove a point. In the Whirlpool galaxy, Messier 51, astronomers found another promising candidate. A cool supergiant had been sitting calmly in archival Hubble images for years. Then, at some point between 2017 and 2019, the star had dimmed by more than 2 magnitudes. Over a factor of 6 in brightness. The dimming was dramatic, sustained, and matched the theoretical predictions for what a collapsing star should look like from the outside: progressive fading, reddening, a slow disappearance into nothing. Excitement built. A second failed supernova candidate, independent of NGC 6946, EH1, in a completely different galaxy. Two candidates in two different galaxies would have been powerful evidence. Then, in 2021, the star came back. Brightness recovered. The supergiant was still there, still burning, still very much alive. And the dimming had not been a collapse. The dimming had been dust. A cloud of material ejected during a violent surface episode had blocked the light from reaching our telescopes. Not a collapse, just a cloud. The behavior was strikingly similar to the great dimming of Betelgeuse in 2019 and 2020. That famous red supergiant in Orion lost roughly 2/3 of visible brightness before recovering months later. Betelgeuse had not collapsed. Betelgeuse had sneezed. A massive blob of hot plasma erupted from the surface, cooled into dust, and temporarily blocked the view. The Whirlpool Galaxy candidate had pulled the same trick. A promising failed supernova candidate evaporated overnight. Astronomers who had been building the case for a second vanishing star had to throw the entire case out. The Betelgeuse comparison deserves a moment. A star 800 light-years away terrified half the internet because Betelgeuse dimmed. And the actual explanation was that Betelgeuse had a bad day and coughed up some dust. That same mechanism fooled professional astronomers, people searching for the most consequential stellar death events in the observable universe. That false alarm matters because the false alarm reveals a hard truth about the search. Distinguishing a star that has genuinely collapsed into a black hole from a star that is briefly obscured by dust is extremely difficult. Both events look the same from a distance. A luminous star dims, fades, and disappears. The difference between death and a dust cloud can only be confirmed by waiting years, sometimes decades, to see whether the star comes back. And even then, certainty remains elusive. Which brings us to the most unsettling result of all. Robert Byrne and Morgan Fraser at University College Dublin built a custom pipeline. The target, 10 years of observations from the Palomar Transient Factory and the Zwicky Transient Facility. The survey covered 231 nearby galaxies. Every algorithm in the pipeline was tuned to find the faint, slow transients that a failed supernova would produce. Stacked images were tracked across years, filtered for exactly the kind of slow dimming that a collapsing star should create. Known supernovae were recovered. Interesting transients turned up, but the number of those transients consistent with a failed supernova was 0. 10 years, 231 galaxies, millions of monitored stars, not a single confirmed case of a star vanishing into a black hole. That now result has two possible explanations, and both explanations are disturbing. Either failed supernovae are genuinely rare, meaning the theoretical prediction that a large fraction of massive stars collapse silently is wrong, or failed supernovae do happen, but the faint optical glow the collapse produces is so dim, so feeble, that our current instruments simply cannot detect the signal. In the first case, the models need serious revision. In the second case, the evidence exists but remains invisible to every telescope we have built so far. Byrne and Fraser calculated upper limits. If failed supernovae are as bright as the models predict, the rate of failed supernovae cannot exceed roughly 23 to 61% of the total core collapse rate. That number depends on assumptions about how bright the events actually are. The Vera-Rubin Observatory will begin surveying the entire southern sky starting in the mid-2020s, and Rubin should detect 1 to 4 failed supernovae per year. Assuming the events are real and the brightness models are correct, if a full decade of Rubin observations passes and the count remains at 0, the theoretical prediction will need fundamental revision. But if the glow is fainter than predicted, if the optical signature of a collapsing star is even dimmer than the theoretical flaw, then these events could be happening all around us, and we would never know. Silence in that scenario would not even qualify as a mystery. Silence would be a permanent condition. The giants are still missing. nobody has found where the biggest stars go when they die. A 25 solar mass star vanished in NGC 6946, and nobody can prove the star became a black hole. One promising candidate in the Whirlpool galaxy turned out to be a dust cloud, pretending to be a death, and a decade-long survey across hundreds of galaxies found nothing. The assumption that bigger should mean louder has been destroyed, replaced by a silence that nobody can explain and nobody can observe. But the frustration of missing evidence was about to become worse, because one team thought they had found the answer. One team celebrated a breakthrough, and then one team discovered that the breakthrough was wrong. But at least someone had made a regular star explode inside a computer. At least one team had cracked the mechanism wide enough to produce a real result. A run where the blast front revived, debris flew outward, and the compact object sat at the center, exactly where the textbook said a neutron star should be. That was the good news, and I believed every word of the good news. So did everyone else in the field. And the good news turned out to be a lie, the team told themselves. Adam Burrows had been chasing stellar explosions for decades, working at Princeton with collaborators David Vartanyan and Tianshu Wang. Burrows ran some of the most sophisticated three-dimensional collapse models ever attempted, using a code called Fornax. The target was a star roughly 23 times the mass of our sun. Solar metallicity, a well-studied progenitor sitting in a mass range where the physics should have been tractable. The run began at the moment of core collapse and tracked the aftermath in full three-dimensional detail, with neutrino transport, turbulent convection, and general relativistic corrections all running simultaneously. The computational cost was extraordinary. Every second of simulated stellar time consumed weeks of real-world supercomputer time. 3 species of neutrinos tracked across 12 energy groups, over 1,000 radial zones, 128 polar angles, 256 azimuthal angles. The code did not simplify the chaos, and the designers never intended for the chaos to simplify the chaos. Fornax attacked the full three-dimensional problem directly, without shortcuts. After roughly 6 seconds, the result looked clear. The blast front had revived. Debris was flying outward. A neutron star sat at the center, with a gravitational mass of about 1.7 solar masses. The energy released was modest but real, roughly half the typical output expected for a core collapse event. Burrows and colleagues declared the run a success and moved on. Publications followed in 2020 and 2024. Over time, the 23 solar mass case joined a growing catalog of simulated stellar deaths, each one a brick in the argument that the delayed neutrino mechanism actually worked. The celebration was genuine. After decades of stalled pressure waves and failed attempts, here was a star that had successfully detonated inside a machine. A compact object left behind fit the expected mass range. The energy released fell within the bounds that observational data demanded. Every box was checked, and the catalog grew. The 23 solar mass result sat alongside a dozen other cases, each one reinforcing the confidence that the community was building around the neutrino mechanism. But here is what nobody asked. What happens after 6 seconds? 6 seconds sounds like a long time in the context of core collapse. The bounce takes milliseconds. Within a fraction of a second, the pressure wave stalls. Over hundreds of milliseconds, the neutrino mechanism kicks in. By 6 seconds, every dramatic event in the standard narrative has already happened. The blast front has revived, a detonation has launched, and a compact object has formed. Declaring victory at 6 seconds felt reasonable. And reasonable is exactly the kind of assumption that buries the truth. Most research groups on the planet had been stopping their calculations even earlier, around 1 second after bounce. The reasoning was practical. 1 second of simulated stellar time in 3 dimensions could burn through months of supercomputer allocation. Universities and national laboratories distributed computing time in fixed blocks, and a single supernova run could consume an entire year's allocation for a research group. Extend that run by a factor of 10, and the group produces no other results. extend by a factor of 1,000, and the group's funding agency starts asking why one calculation needs more resources than entire departments. The incentive structure pushed every team toward the same decision: watch the exciting part, record the output, and stop. Burroughs and the Princeton group eventually did something that almost nobody else had done. They kept the camera rolling. Instead of stopping the calculation at 6 seconds, the team mapped the Fornax output into a different code called Flash, a hydrodynamics tool capable of tracking the aftermath over much longer timescales. The handoff was delicate. The full output of the three-dimensional Fornax run, every velocity field, every density profile, every temperature gradient, transferred into a new code with different numerical methods and a different equation of state. Getting that transition smooth, with no artificial shocks or discontinuities at the boundary, required careful engineering. An outflow boundary condition, constructed from the actual flow properties observed in the Fornax calculation, ensured that the physics continued seamlessly. The juncture sat exterior to the sonic point of the flow. Nothing about the handoff was trivial, but the team wanted to see what happened next, over hours and days. Precisely the kind of timescales that nobody had bothered to examine, because everyone assumed the interesting physics was finished. The physics was not finished. Within 50 seconds of bounce, an additional 0.45 solar masses of matter had quietly reversed course and fallen back onto the central object. Debris that had been hurled outward during the initial outburst, debris that every observer would have counted as ejecta, slowed down, stalled, and turned around. The outer envelope of the dying star was too heavy, too tightly bound. The outburst had not been strong enough to clear the returning matter permanently, and the fallback did not stop at 50 seconds. Over the next 1,000 seconds, roughly 17 minutes of stellar time, the returning matter grew to roughly 2.4 solar masses. The compact object that everyone had celebrated, the product that was supposed to be the final outcome of the successful detonation, was being buried alive. Picture what the star looked like during those 17 minutes, simultaneously exploding and collapsing. In one direction, pressure waves raced outward through the stellar envelope, carrying radioactive nickel forged in the detonation, punching through layers of silicon and oxygen and helium. In another direction, at the same moment, dense plumes of matter were falling inward, decelerating after the initial burst, reversing and streaming back toward the center. The star was dying two different deaths at the same time. That simultaneous eruption and accretion, that image of a star ripping apart in one hemisphere while collapsing in another, cannot be captured in a one-dimensional calculation. Only 3 dimensions can capture the phenomenon. Real stellar death is not a keen outward pulse. What actually unfolds is a chaotic, asymmetric war between forces that barely differ in strength. By the time the run reached 300,000 seconds, roughly 3.5 days of stellar time, the remnant had swallowed enough returning matter to push past the breaking point. A neutron star can only hold so much mass before gravity overwhelms every force that keeps the object from collapsing further. That limit has a name: the Tolman-Oppenheimer-Volkoff limit, named in part after the same Oppenheimer who, years before building the atomic bomb, co-authored the first serious proposal that a star could collapse into what we now call a black hole. In 1939, Oppenheimer and Hartland Schneider calculated that a sufficiently massive core, stripped of all pressure support, would contract without limit. The mathematics of general relativity demanded the result. Oppenheimer moved on to other work. The space-time he described as a mathematical consequence had become, 8 decades later, the fate of a simulated star that was supposed to have exploded successfully. Cross the Tolman-Oppenheimer-Volkoff limit, and the neutron star has no choice. The object falls into darkness. Roughly 4.9 solar masses of matter, wrapped into a region of space-time from which nothing escapes. The 23 solar mass star had detonated. A real stellar death event had occurred, ejecting roughly 9.9 solar masses of debris with an energy of about 0.46 Bethes. Radioactive nickel was forged in the outburst, roughly 0.04 solar masses ejected into space. From the outside, the event would have looked like a normal supernova. Telescopes would have detected the flash. Spectrographs would have measured the expanding wreckage. Every instrument pointed at that event would have recorded a successful outcome. And hiding at the center of all that light, where a compact object was supposed to be sitting, a dark remnant had quietly formed while everyone was watching the fireworks. The Princeton group had to revise their own published result. Gone was the compact object they had reported. The explosion they had celebrated was real, but the ending was different from the ending they had announced. A star that appeared to die in a textbook fashion, outburst followed by compact object, had actually died in a way that nobody had predicted. Explosion followed by a slow, invisible betrayal, where the returning matter fell back and swallowed the evidence. The universe had produced a record of the event, a bright flash, a debris field, every sign of a successful death, and then quietly erased the truth behind the spectacle. I want to make sure you understand why this matters for the entire field, far beyond one case. The Princeton group was not sloppy. Burroughs and Vartignan are among the most careful, most experienced supernova modelers on the planet. The code is one of the most advanced modeling tools ever constructed for this problem. The 23 solar mass progenitor was not a fringe case or a corner of parameter space where odd outcomes cluster. That progenitor sat in the middle of the mass range, where core collapse occurs. And the error, if you can even call the error an error, was stopping the calculation at 6 seconds. The physics after 6 seconds changes the outcome from compact object to gravitational collapse. Everything that happened before 6 seconds was real. The revival was real, and so was the outward burst that followed. The eruption was genuine, but the story did not end where the run ended. The outcome had a second chapter that nobody witnessed. And that pattern, stopping the calculation too early, was not unique to the 23 solar mass progenitor. The same group had run a 40 solar mass star through the code and initially estimated the final collapsed object mass at roughly 3.5 solar masses. The results looked complete at around 21 seconds after bounce. By that point, the mean shockwave radius had expanded to 200,000 kilometers. Accretion appeared to be subsiding. Every diagnostic suggested the system was settling into a final state. When the team extended the simulation, mapping the output into flash and running for hours of stellar time, the answer changed dramatically. Binding energy in the outer mantle, layers of helium and hydrogen that the outburst had not fully unbound, maintained a steady stream of debris falling back toward the center. That fallback followed a predictable mathematical decay, a power law that dropped slowly over time but never stopped. The asymptotic mass of the dark object was not 3.5 solar masses. The final mass was approximately 9 solar masses, nearly 3 times the original estimate. A dark remnant that would have been classified as modest by the early calculation turned out to be one of the heavier stellar mass collapsed objects in the entire catalog. Ejector mass dropped to roughly 6.2 solar masses. Meanwhile, the energy released held steady at roughly 1.75 Beths, a vigorous eruption by any standard. But that vigorous eruption had not been powerful enough to prevent nearly 9 solar masses of matter from falling back into darkness. The implications cut across every published result in the field. Most three-dimensional collapse simulations across every research group on the planet had been stopped at roughly 1 second after bounce. 1 second! For the 23 solar mass progenitor, the outcome changed between 6 seconds and 300,000 seconds. For the 40 solar mass case, the remnant mass tripled over hours. And nobody knew what the other published runs would reveal if someone extended those models to comparable timescales. Every successful outcome in the literature, every remnant mass estimate, every energy measurement came with an invisible asterisk. The asterisk said, assuming nothing important happens after we stopped watching. Everyone in the field had been leaving the theater before the final plot twist arrived. Why? That habit of cutting simulations short was not born from laziness or negligence. Running a three-dimensional collapse model for 1 second of stellar time requires extraordinary computing resources. National supercomputers operating for months on a single case. Millions of processor hours consumed before a single output can be analyzed. Extending a single run from 1 second to 1 day of stellar time multiplies the cost by orders of magnitude. Research groups working under pressure to publish, competing for telescope time and grant funding, made the rational choice to stop at the point where the most dramatic physics appeared to be finished. The blast front had revived. The outward burst had launched. Declaring success at that moment was the sensible decision, and the sensible decision was wrong. The 23 solar mass star was supposed to be a victory, a tidy example of the neutrino mechanism working as predicted, a successful outcome leaving behind a well-behaved neutron star. Instead, the star became a cautionary tale about what happens when scientists stop watching too soon. The explosion was real, and the neutron star that formed at the center was equally real. But that neutron star was temporary, a structure that existed for minutes, radiating neutrinos and gravitational waves exactly like a stable remnant should, before vanishing behind an event horizon that had been forming in slow motion the entire time. Here is the detail that should keep any honest scientist awake at night. The stellar death produced by the 23 solar mass star would have been virtually indistinguishable from an event that left behind a permanent neutron star. Same flash and same wreckage. Identical chemical spectrum, with matching radioactive glow from nickel decay in the expanding shell. A telescope pointed at that event, using every instrument currently available to modern astronomy, would have recorded a normal core collapse death and moved on. Nobody would have suspected that the object at the center was a black hole instead of a stable neutron star. How many stellar deaths might be hiding black holes behind perfectly normal-looking events remains unknown. Burroughs and colleagues speculated that the pathway could account for dark objects ranging from roughly 3 to 10 solar masses. That range overlaps with the most commonly observed black holes in X-ray binary systems. Every one of those observed dark objects might have been born behind the cover of a stellar death that fooled every telescope watching. The betrayal runs deeper than one wrong case. What haunts the field is that the real universe might be producing these events constantly, and every telescope aimed at the sky cannot tell the difference. The celebration was premature. The result everyone trusted was a mirage. And if the team that found the answer discovered their own answer was wrong, the next question becomes far more uncomfortable, because the boundary between the outcomes is razor thin. A star that leaves behind a neutron star and a star that is completely annihilated, separated by almost nothing. And the objects that should not exist, according to confident predictions, keep showing up where nobody expected to find them. Almost nothing. That is the phrase I keep coming back to. The boundary between a star that collapses into a black hole and a star that detonates so completely that nothing survives. Not a remnant, not a neutron star, not even darkness. That boundary is separated by almost nothing. And I need you to understand how thin that line actually is, because the physics behind the line is so extreme that the entire concept of a keen prediction falls apart when you look closely. Start with a star, not a regular star, not even close, a monster. 80 solar masses at birth, maybe 100, maybe 140. Stars. This massive burn through hydrogen so fast that the interior reaches temperatures most of the universe will never experience. Deep inside the core, after the helium has been fused into carbon and oxygen, the temperature climbs past 1 billion degrees. At those temperatures, a strange threshold is crossed. The light itself, the photons carrying radiation pressure that hold the star up against gravity, those photons become so energetic that they spontaneously transform into pairs of matter and antimatter, an electron and a positron, conjured from pure light. That process has a name: pair production. And pair production is a thief. Every photon that converts into a particle pair is a photon no longer pushing outward against gravity. The radiation pressure that keeps the core from collapsing drops, the core contracts. Contraction raises the temperature. Higher temperature produces more pairs. More pairs steal more pressure. The feedback loop has no ceiling. The star is eating itself from the inside. What happens next depends on one variable: mass. And the outcomes on either side of a single mass threshold are so different that they might as well belong to different universes. For a helium core around 62 solar masses, the pair instability triggers explosive oxygen burning. The core convulses. A violent pulse rips through the interior, ejecting material outward. But the pulse is not strong enough to destroy the star. The core survives. Material falls back. Over the course of hours, days, sometimes weeks, repeated pulses strip mass from the dying star, each one weaker than the last, until the core finally runs out of fuel and collapses into a black hole. The final object weighs roughly 50 solar masses. Massive, dark, permanent. Researchers call the process pulsational pair instability. The star rips pieces of itself away in episodes, like a building shedding floors during an earthquake before the foundation gives out and the whole structure drops into the basement. Picture what the star looks like during those weeks of pulsation. The core contracts violently, heats beyond the threshold where photons shatter into particle pairs, and ignites a thermonuclear blast. The blast races outward, slamming into the outer layers, launching shells of material into space at thousands of kilometers per second. Then the blast fades, gravity reasserts control, the core contracts again, more pair production. Another pulse, another ejection. Each cycle strips roughly 3 to 13 solar masses of material from the star. Xinqi Leng and Kenichi Nomoto at the Kavli Institute for the Physics and Mathematics of the Universe in Tokyo calculated the hydrodynamics of these pulsations in detail. The timescales between pulses can stretch from weeks to years, depending on the mass. Between ejections, the star sits quietly, a ticking bomb that has already detonated multiple times, but has not yet finished dying. Cumulative mass loss from all the pulsations is what determines the final black hole mass. Strip enough material, and the core that eventually collapses is lighter. The physics is brutal, but orderly. Brutal because each pulsation is a thermonuclear detonation powerful enough to rival a supernova. Orderly because the process always ends the same way. The core runs out of fuel. Iron accumulates. Gravity wins. A black hole forms. The pulsational pair instability channel sets a ceiling on the black hole mass. That ceiling, according to the calculations, sat at roughly 50 solar masses. Nothing heavier should form through this channel. Now add 2 solar masses, just 2. Move from 62 to 64 solar masses of helium core. The pair instability triggers again. Explosive oxygen burning ignites again, but the energy released is enough. The nuclear detonation overwhelms gravity entirely. No convulsion, no pulsation, just an explosion, completely. Every atom scattered, no black hole forms, no neutron star forms, nothing remains. Total annihilation. The technical name is a pair instability supernova. The explosion is so powerful that a single event can briefly rival the luminosity of an entire galaxy. And where the star used to be, the space is empty. Not dark, not collapsed, just vacant. The star has been converted into kinetic energy and light, dispersed across light years, leaving zero compact remnant behind. 2 solar masses, that is the margin. At 62, a 50 solar mass black hole sits in the darkness. At 64, absolute zero. Nothing. The difference between the heaviest kind of darkness and the lightest kind of nothing is almost nothing. I want you to hold that picture because the picture gets worse. Stan Woosley at the University of California, Santa Cruz, had been calculating the fates of massive stars for decades. Working with the Kepler Stellar Evolution Code, Woosley built model after model, tracking how stars of different masses, compositions, and rotation rates evolve through the pair instability. The calculations were demanding. Each model required tracking thousands of mass shells following nuclear, burning through dozens of isotopes, resolving the dynamics of pulsations that could last for years of stellar time. Woosley kept a single calibration choice constant for over 25 years. One number, the rate at which carbon-12 captures a helium nucleus to become oxygen. 16. That reaction rate, characterized by a quantity physicists call the S factor, essentially a scorecard measuring how eagerly 2 nuclei merge when they collide. determines how much carbon is left in the core after helium burning finishes. And how much carbon is left determines how the pair instability unfolds. More carbon means weaker pulsations. Less carbon means stronger pulsations. The boundary between pulsational pair instability, where a black hole forms, and full pair instability, where the star is annihilated, shifts depending on that single number. Woosley chose a specific calibration value in 1993, drawn from laboratory measurements of the reaction cross-section, filtered through nucleosynthesis constraints that favored a relatively high rate. And then he never changed the number. For 25 years, that same value anchored every calculation. Partly because the value worked, partly because changing the calibration would make comparisons between decades of published papers impossible. Every prediction of maximum black hole mass, every estimate of where the mass gap begins, every calculation of which stars could form black holes and which would be completely destroyed, flowed downstream from the choice of a single researcher, a single number measured in a particle accelerator on Earth. Then new laboratory measurements arrived. Kibedi and colleagues, and separately Erickson and colleagues, measured a key component of the triple alpha reaction rate, the process that determines how much carbon is produced during helium burning. That new measurement came in roughly 35% higher than the value the field had been using. 35%! Outside the previous error bar. A shift that large, propagated through the pair instability calculations, moves the boundary of the mass gap by more than 10 solar masses. At the old calibration, the maximum black hole mass from pulsational pair instability sat near 50 solar masses. At the new calibration, the maximum climbs towards 64 solar masses. The forbidden zone, the range of masses where pair instability should prevent any black hole from forming, had been treated as a clean feature of stellar physics for nearly 2 decades. Sharp walls, solid floor, and a single laboratory measurement made by a small group of nuclear physicists working with a particle accelerator moved the walls by a distance comparable to the mass of dozens of suns. That is the sensitivity. A number measured in a basement laboratory, adjusted by 35%, shifts the predicted fate of a star 10,000 light-years away from silent darkness to total annihilation. Think about what that means for every published prediction in the field. Every paper that stated the maximum black hole mass from pulsational pair instability is approximately 50 solar masses was downstream of a calibration choice that one researcher made in 1993 and kept for a quarter century. Not because the choice was wrong, because the choice was practical. And practicality. In a field where 2 solar masses separate total darkness from total destruction, turns out to be a dangerous substitute for certainty. That entire map of which stars produce black holes and which stars are annihilated was drawn with a pencil whose tip was wider than the features the map claimed to resolve. The universe does not adjust the physics to match the precision of human instruments. The boundary exists at whatever sharpness nature chose, and the question of whether we can ever measure the boundary clearly enough to predict outcomes is not a technical problem. The question is whether the universe permits prediction at all on a cliff edge this narrow. But the forbidden zone was supposed to be more than a prediction. The zone was supposed to be empty. Between roughly 50 and 130 solar masses, pair instability should prevent any black hole from existing. Stars below the lower boundary collapse into black holes through pulsational pair instability. Stars above the upper boundary are so massive that the pair instability cannot disrupt the entire star, and the core collapses into a black hole so heavy that the object sits above the gap. But inside the gap, nothing. No formation channel, no physical mechanism. Pair instability either strips the star down to a black hole below 50 solar masses or destroys the star entirely. No black hole should be sitting at 60 or 70 or 85 solar masses. The prediction was considered robust. The physics was fundamental. Electron-positron pair production from energetic photons is a direct consequence of quantum electrodynamics, one of the most precisely tested theories in all of science. That gap was not a guess. That gap was a consequence of physics, verified to 12 decimal places in laboratory experiments. Then the gravitational wave detectors started weighing black holes. In September of 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected the merger of two black holes for the first time in human history. The event, designated GW1 50914, involved two black holes with masses of roughly 36 and 29 solar masses. Both sat comfortably below the predicted mass gap. No problem. More detections followed. GW151226, GW170104. Each merger involved black holes within the expected mass range. The gap held. The prediction survived. Then GW190521 arrived. The signal was detected on May 21, 2019. One of the merging black holes weighed roughly 85 solar masses, sitting squarely in the middle of the forbidden zone. A black hole that should not exist, according to every pair instability calculation published in the previous 2 decades, had been caught in the act of merging with another black hole. No ambiguity in the detection. Clean signal. The mass estimate carried error bars, but even the lower bound placed the object well inside the gap. Nobody could dismiss the measurement as noise. The catalogue grew. The third gravitational wave transient catalogue, published by the LIGO, Virgo, and CAGRA collaborations, contained dozens of merging black hole pairs. Multiple objects showed component masses at 60, 65, even 70 solar masses, not one outlier, a population. Black holes were living inside the forbidden zone, paying rent and refusing to leave. Remember the patchwork Evan O'Connor and Christian Ott found when mapping which stars explode and which collapse silently? The islands of explodability? The mass gap was supposed to be different. That mass gap was not a patchwork. That mass gap was a desert, a clean, empty stretch of the black hole mass spectrum, enforced by fundamental physics where nothing should grow. And suddenly, the desert had inhabitants. The community had to ask a question that nobody wanted to ask. Were those inhabitants real, or were the measurements wrong? The signal from GW190521 was analyzed and reanalyzed. Independent groups confirmed the mass estimate. The inhabitants were real. That gap had not been disproven. Fundamental physics remained correct. Pair production still happens. Explosive oxygen burning still occurs. Stars in the right mass range are still destroyed. But the boundaries of the gap, the clean walls that everyone had drawn with confidence, turned out to be far softer, far more uncertain, and far more permeable than anyone had appreciated. Reaction rate uncertainties alone could shift the lower boundary from 50 to 64 solar masses. Rotation could push the boundary further. Binary evolution could push the boundary further still. Hyper-Eddington accretion, after a black hole forms, could add mass that climbs the object into the gap from below. The gap might still exist. But what remains is not a chasm with vertical walls. The gap is a shallow valley with gently sloping sides, and objects keep wandering across the slopes. Ousley and Alexander Heger, working at Monash University, published an analysis examining all 4 factors simultaneously: variable reaction rates, detached binary evolution, rotation, super-Eddington accretion. The conclusion was measured, but devastating for clean predictions. Current uncertainties in reaction rates alone allow the lower boundary of the mass gap to rise from 50 to 64 solar masses. The upper boundary could shift from 130 to 161 solar masses. Adding rotation could push the lower boundary past 70 solar masses. Adding binary evolution and accretion pushes the boundary further into territory that nobody had mapped. The mass gap that was supposed to be a hard feature of the universe, a direct consequence of one of the most fundamental theories in physics, had become a soft, uncertain, porous boundary whose exact location depends on laboratory measurements that nobody has nailed down. I want to put that in human terms. A nuclear physicist adjusts a calibration on a particle accelerator. The adjustment changes the measured rate of a reaction. That happens inside the cores of dying stars. That change propagates through stellar evolution codes. The codes recalculate which stars produce black holes and which stars are completely destroyed. The maximum mass of a black hole shifts by more than 10 solar masses. A star on the other side of the galaxy, a star that no human being will ever visit, switches from producing a 50 solar mass region of space-time from which nothing escapes, to producing a violent flash of light that destroys every atom and leaves nothing behind. The fate of that star depends on a number measured in a laboratory, and the laboratory is not settled on the number. That is vertigo. Not the kind where you look down from a height. The kind where you realize the ground was never solid. The assumption that physics should produce clean boundaries between outcomes, that there should be a slope connecting one fate to another, was wrong. Nature drew a cliff, and the location of the cliff depends on measurements that are still changing. The objects that should not exist keep appearing. The forbidden zone that should be empty keeps accumulating residents. And the boundary between total destruction and total silence, between a black hole that swallows everything and an explosion that leaves nothing, is separated by a margin so thin that a single laboratory calibration can flip the outcome. The confident prediction was not wrong in principle. The confident prediction was wrong in precision, and in a universe where two solar masses separate everything from nothing, precision is the only currency that matters. The boundary is not a slope. The boundary is a cliff, and objects keep appearing on the wrong side. Every thread has pulled toward the same place. Broken simulations and invisible deaths, a celebrated answer that collapsed under the weight of extended observation. A cliff edge separating total darkness from total annihilation, where two solar masses decide between everything and nothing. And now, one final question remains. Can we predict which fate awaits a given star? I have been dreading the answer because the evidence we have gathered, every piece of the record, points in a direction that nobody wants to face honestly. The answer is no. We cannot predict the outcome. Not roughly, not reliably, and certainly not to the correct order of magnitude for the mass of the final object. And I need to show you exactly why the prediction breaks down, because the failure is not a matter of needing better telescopes or faster computers. The failure sits inside the physics. The machinery of prediction depends on inputs that nobody has nailed down, running through codes that nobody fully trusts, producing outputs that change depending on choices that nobody can justify from first principles. Start with the inputs. Every prediction about which stars explode and which stars vanish begins with one structure: the stellar core at the moment of collapse. That core, the density profile, the composition, the arrangement of burning shells, is the product of millions of years of nuclear burning, compressed into a single snapshot taken at the moment gravity wins. And the snapshot is sensitive to nuclear reaction rates that carry large uncertainties. We covered one of those rates already, the carbon-12 alpha capture rate that Woolsey held constant for 25 years. But the sensitivity does not stop at a single reaction. Shell burning, convective mixing, the interplay between silicon and oxygen burning in the final hours before collapse, each of those processes depends on nuclear cross-sections measured in labs, and those measurements carry error bars that propagate downstream into the models with devastating effect. Fabian Schneider and colleagues, working at the Heidelberg Institute for Theoretical Studies, mapped the full range of massive star endpoints across initial masses and compositions. The mapping was not a prediction. The mapping was an exercise in documenting carefully how many different answers the same question could produce. Change the nuclear equation of state and the maximum mass for the compressed core shifts. That shift changes which stars cross the threshold into dark object territory. Change the composition, and the star loses less mass to stellar winds during millions of years of evolution, arriving at collapse with a heavier envelope. Heavier envelopes mean more material available for fallback. More fallback means heavier final objects. Schneider's mapping showed clearly that the relationship between birth mass and final fate for any given star was not a function. The relationship was a cloud, a scatterplot of outcomes so noisy that two stars born with nearly identical masses could end in completely different ways. The variables that determine the outcome cannot be constrained from observations alone. Nobody can look at a star through a telescope, measure the star's mass and brightness, and predict with confidence whether that particular star will explode or vanish. The input data carries too much uncertainty. The models respond to that uncertainty with wildly different answers, and the outcomes scatter across the mass spectrum in patterns too chaotic to form a reliable map. And the codes themselves introduce a second layer of uncertainty. Every collapse calculation involves approximations, and the choices matter enormously. How particle transport is handled, whether turbulence is fully resolved or merely simplified with shortcuts, how the nuclear equation of state is implemented at densities beyond what any lab can reproduce. Different research groups, using different codes with different shortcuts, produce different answers for the same starting star. Adam Burrows at Princeton, using Fornax, finds that a 40 solar mass star explodes vigorously and leaves behind a dark remnant through fallback. Other groups, using different codes and different physics choices, find that the same 40 solar mass star collapses silently with no explosion at all. The starting conditions are identical, same mass, same composition profile, identical down to the isotope level, and yet different codes, running different methods, produce different outcomes entirely. Neither group can prove the other wrong, because no experiment on Earth can settle the dispute. Nobody can tell you which code is correct, because the physical conditions inside a collapsing stellar core are so extreme, so far beyond any laboratory on Earth, that no experiment can reproduce the environment directly. I want to put a number on the problem, because numbers make the scale of the uncertainty real. Burrows and colleagues ran a collection of three-dimensional models, and the results revealed something that should have been simple but was not. The same type of dark object can be born in completely different ways, and each pathway looks different from the outside. Start with the loudest version. A vigorous, asymmetric explosion rips the star apart. Debris flies outward, and every telescope in the area records a successful detonation. But accretion onto the proto-object at the center pushes the core past the breaking point before the blast clears. The star explodes and forms a dark remnant simultaneously. Dial the energy down, and the scenario gets sneakier. A modest blast ejects material, but not enough to prevent the core from crossing the threshold. From the outside, the event looks like a routine catalog entry. Nobody would suspect the truth, hiding behind a perfectly ordinary flash. Now strip the explosion almost entirely. The shockwave launches, gains some ground, but the accretion rate is so high, so relentless, that the collapsed object forms within hundreds of milliseconds. The newly formed object swallows the engine that was driving the blast, and the shockwave reverses. Material that had been heading outward falls back inward. For the most massive cases, the final object grows to 30, even 40 solar masses by consuming the entire stellar envelope. And at the far end of the spectrum sits the scenario everyone imagined first, the silent collapse. No explosion occurs. No shockwave ever revives. The star simply dims, fades below detection, and vanishes. Here is the part that haunts the investigation. Burrows speculated, based on those models, that the silent scenario might not even be the dominant formation path. Most stellar mass dark remnants might be born not in silence, but behind the cover of a real explosion. If that speculation holds, then the entire observational record of stellar deaths needs re-examination. Every telescope that catalogued a normal detonation and moved on may have missed a dark object forming at the center while astronomers celebrated the flash. 4 pathways. 4 different ways a star can produce the same type of object, and the mapping between starting conditions and final channel, when examined closely, is so chaotic that nobody can draw a clean prediction. The compactness parameter that Evan O'Connor introduced, the single number that was supposed to separate exploding stars from collapsing ones, captures the broad trend, but the real physics depends on the entire density profile of the stellar core, a function with structure on scales that a single number cannot represent. 2 stars with identical compactness values can end up in different channels because a subtle difference in the arrangement of burning shells tips the balance at the critical moment. And sitting behind every calculation, unresolved, is a question that nobody in the field has settled. How long do you need to run the model? We saw what happened to the 23 solar mass case when the Princeton group extended the run from 6 seconds to 3.5 days. The answer changed from stable core to collapsed object. How many other published results would change? If someone extended those calculations by the same factor, nobody knows. The cost of extending any single run to full resolution remains beyond what most groups can justify. The result is a literature full of answers that might be wrong with no practical way to check. Now, add the observational side of the problem. 10 years of searching across 231 galaxies. 0 confirmed silent collapses. The null result from Byrne and Fraser already delivered a verdict, and the verdict was silence. 0. The rate constraint sits between 23 and 61% of all core collapse events, but the constraint is loose. The brightness of a collapsing star remains uncertain. If the glow is even modestly fainter than predicted, current surveys would miss every single event. The Vera Rubin Observatory represents the field's best chance, an 8.4-meter mirror on a mountaintop in Chile, designed to photograph the entire southern sky every 3 nights. No other telescope in history has combined that combination of depth and cadence. And that chance requires another decade of waiting, starting from a count that has not moved from 0. The weight of that waiting is difficult to overstate. Somewhere in the world, a graduate student is defending a thesis proposal built around a detection that may never arrive. The student will spend years designing pipelines, tuning algorithms, filtering false alarms, scanning images from hundreds of galaxies, all in pursuit of a single faint dimming that confirms what the models predict. If the detection comes, the student rewrites the field. If the detection does not come, the student has spent a decade proving that either the theory is wrong or the evidence is permanently invisible. Nobody entering the field today doubts that these events happen. Models strongly predict that a fraction of massive stars collapse without visible explosions. What remains unknown is whether the fraction is large enough and the glow is bright enough for any current or planned telescope to catch a single example. Should a full decade pass with the count still at 0, only 2 explanations survive. Either silent collapses are so rare that the theoretical framework is fundamentally wrong, or the events are happening constantly, producing signals so faint that the most powerful instruments ever built cannot catch the glow. One answer demands rewriting the theory. The other means the answer may sit permanently beyond the reach of any instrument we know how to build. But here is the detail that changed how I think about this entire investigation. Buried inside the physics of core collapse, inside every model from every research group, is a fact that almost nobody discusses in public. Every stellar mass dark remnant born from a dying star must first become a neutron star. Every single one. First, the inner core collapses, bounces, and forms a proto-object. That compressed core sits at the center of the dying star, radiating particles and gravitational waves, behaving exactly like a neutron star should. But the object does not know, cannot know, that the outer core will eventually crush the structure past the breaking point. Information cannot travel fast enough. The speed of sound inside the compressed core sets a hard physical limit on how quickly the object can respond to changes in the surrounding environment. Material falling inward from the outer layers has not yet reached the center. So for a brief interval, lasting anywhere from milliseconds to a handful of seconds, a genuine neutron star exists, complete with a particle signal that a detector like Super Kamiokande could, in principle, observe, complete with a gravitational wave signature that detectors like LIGO could, in principle, measure. And then the neutron star vanishes. Accumulated mass crosses the Tolman-Oppenheimer-Volkoff limit, and the object collapses behind an event horizon. The particle signal cuts off abruptly. Gravitational wave signatures change character, and where a neutron star sat moments before, a dark remnant has taken the place. That transient phase carries a profound implication, one that reshapes the idea of a purely silent collapse. Before becoming a collapsed object, every one of those dark remnants spent a brief moment as a detectable structure, a signal source that broadcast particles and gravitational waves before disappearing forever. Even a failed explosion, one where the shockwave never revives and no blast occurs, still produces a massive burst of escaping particles. The energy radiated during that brief detectable phase is staggering. Roughly 10 to 40% of our sun's entire mass, converted into pure energy, carried away by particles that barely interact with matter. That burst can gently peel off the outermost layers of the dying star, ejecting a thin shell of hydrogen into space. Not an explosion, not even close. A glow far fainter, dimmer by orders of magnitude. But not nothing. A faint, red transient lasting weeks to months, dimmer than a normal stellar detonation by orders of magnitude, but present. Detectable, in principle, if you know where to look and have sensitive enough instruments. The purely silent death, the one where absolutely nothing escapes, may not exist. Every collapse produces a particle burst. That burst carries energy, and that energy peels away at least a thin layer of material. The silent death that everyone imagined, the star that winks out with zero output, zero trace, zero evidence, might be physically impossible. Total silence is a fantasy, one that the physics will not permit. What remains is a whisper, very, very quiet. And the difference between total silence and near silence, between an unsolvable mystery and one that merely requires better instruments, changes the entire picture. I started this investigation with a simple question: how do these objects form from dying stars? The answer turned out to be far messier, far more uncertain, and far more humbling than anything I expected. Nobody can reproduce the simplest version of the explosion inside a computer without first unlocking the chaos of 3 dimensions. The biggest stars die in ways that invert every assumption about size and spectacle. A team that thought they had found the answer had to revise the answer when they finally watched long enough. The margin between outcomes remains so thin that a single calibration choice flips the prediction. And after all of that, we still cannot predict which fate awaits a given star. The search found nothing. 0 confirmed cases of a star vanishing into darkness. The question of how these objects are born is still open, and the silence that everyone assumed was absolute might turn out to be a whisper that nobody has been listening for. So, how much of this is true? I have spent this entire investigation building a case that the biggest deaths in the universe are invisible. That prediction is beyond our reach, that the computational tools are fragile, the observational record is barren, and the margin separating one outcome from another is razor thin. A laboratory adjustment can redirect the destiny of a distant star. The case is compelling. The evidence stacks up from multiple independent directions. But compelling is not the same as proven, and I owe you an honest answer before we close the file. Because some of what we covered is rock solid. Some of what we covered is possible but unconfirmed, and some of what we covered is genuinely unknown, sitting in a territory where nobody alive can tell you the truth. Separating those 3 categories is the only task that matters now. So let me do what I always do at this point. Let me take every piece of evidence we assembled, hold each piece up to the light, and tell you what survives. Start with the garbage. Every field that touches black holes attracts noise, and the noise needs to be cleared before the signal can be evaluated. The first piece of garbage is the popular claim that black holes are cosmic vacuum cleaners. The claim says these objects suck up everything nearby. That image is wrong. A black hole with the same mass as our sun would exert the same gravitational pull. At the same distance, the force is identical. The Earth would orbit a solar mass black hole the same way the Earth orbits the sun right now. Nothing gets sucked in that was not already on a collision course. The vacuum cleaner image distorts how people think about stellar death, because the image implies that a collapsing star creates some new, exotic gravitational monster. No new gravitational force comes into existence. All that changes is geometry, the same mass squeezed into a smaller volume. At any ordinary orbital distance, gravity behaves identically. What changes is the boundary. Cross a certain distance from the center and escape becomes impossible. But at the orbital distances that matter for astronomy, the black hole behaves like any other object of the same mass. The drama is local, not cosmic. The second piece of garbage is the idea that a failed supernova means the star blinks out like a light switch. That framing misrepresents the physics in a way that sounds dramatic but misleads the audience. A massive star collapsing into a black hole does not vanish in an instant. The process takes time. The outer layers of the star, the hydrogen envelope, the helium shell, those layers do not know the core has collapsed. Information travels at the speed of sound inside the star, and the speed of sound is finite. The outer envelope continues burning, continues radiating, continues behaving like a normal star for hours to days. The core has already crossed the point of no return. From the outside, the star does not blink. The star dims, slowly, over weeks to months, a faint red transient declining in brightness, fading below detection limits. That slow fade is the observational signature that Kochenek and colleagues at Ohio State designed their survey to detect. Not a blink, a whisper. The difference matters because the difference determines what instruments can catch the signal and what instruments cannot. A third piece of noise is less a hoax and more a persistent misframing. Popular science writing treats the phrase mass gap as though the gap is a proven, permanent feature of the universe, as though nothing exists between 50 and 130 solar masses, period, full stop, case closed. We covered the gap extensively when we examined the cliff edge between destruction and silence. The physics behind pair instability is real, verified by some of the most precisely tested quantum mechanics in existence. But the location of the boundaries depends on nuclear reaction rates that carry significant uncertainties. The walls of the gap are soft. The boundaries shift by more than 10 solar masses depending on which calibration you use, and gravitational wave detections have placed black holes squarely inside the predicted gap. The gap exists as a theoretical prediction. The gap does not exist as a clean, hard boundary confirmed by observation. Anyone who presents the mass gap as a settled, resolved feature of nature, with sharp walls and no residence, is overstating the evidence. The honest framing is that pair instability creates a region where black hole formation becomes increasingly difficult. The edges of that region remain uncertain, and observed black holes have wandered across those edges repeatedly. Now, with the garbage cleared, let me show you what the evidence actually supports, because the honest picture is more interesting than the noise. The broken mechanism is proven. 50 years of spherical simulations failed to produce a stellar explosion. That failure is documented across decades of published work, from Colgate and White in 1966 through the modern era. The reason for the failure is understood. Spherical symmetry, the assumption that the explosion expands equally in all directions, suppresses the turbulence and convection that the real mechanism requires. Once computing power allowed full three-dimensional calculations where the collapse could be messy, lopsided, and turbulent, certain stellar models finally detonated. Not every run, not with guaranteed outcomes, but the pattern linking flat symmetry to dead shock waves and broken symmetry to revived explosions stands on decades of converging evidence from independent teams. That connection rests on decades of independent work. Multiple groups, using different codes and different physics, reached the same conclusion. The driving force is neutrino heating. Particles escaping the newborn core surrender a fraction of their colossal energy. That energy transfers to the material sitting behind the stagnant blast front, and that thermal injection, magnified by chaotic convective motion, reignites the outward push. The mechanism operates on a narrow margin. Roughly 5% of the neutrino energy needs to be absorbed, but that 5% carries enough force to revive the blast. The delayed neutrino-driven mechanism is not a speculation. The mechanism is the leading theoretical framework, supported by multiple independent simulation campaigns, and the mechanism explains the broad patterns of observed supernova properties. What remains unproven is whether the mechanism works for every star, and whether the specific outcomes produced by any given code match what nature actually does. The invisible deaths are possible, but unconfirmed. Computational models from multiple research groups converge on a shared conclusion. A portion of the heaviest stars cave in without generating any detectable blast. Multiple independent arguments support the prediction. O'Connor and Ott showed that tightly packed cores resist disruption, making silent collapse more likely at higher compactness values. SMART documented a conspicuous absence. No confirmed supernova progenitor above 17 solar masses has ever been identified, suggesting that the heaviest stars exit the stage without producing a standard detonation. And the single strongest candidate, NGC 6946b1, presents a 25 solar mass star that brightened, faded, and vanished without producing any detected explosion. But the candidate remains unconfirmed. No black hole has been directly detected at that position. No infrared accretion signal has been found. And the second strongest candidate, a dimming supergiant in the Whirlpool galaxy, recovered, alive and burning, after what turned out to be nothing more than ejected dust blocking the view. The 10-year survey across 231 galaxies found 0 confirmed cases. That null result is real and significant. Byrne and Fraser placed upper bounds on how often these quiet collapses occur, arriving at a range of roughly 1/4 to 3/5 of all core collapse events. The exact number hinges on assumptions about the luminosity floor of the fading signal. But a null result from 0 confirmed detections is not proof that silent collapses never happen. The null result means either the events are rare or the events are too faint for current instruments. Both explanations remain viable. Neither has been eliminated. Here is where the honest assessment gets uncomfortable, because the next category is genuinely unknown, and the territory covered by that label is vast. We do not know the exact boundary between explosion and silence. The models are sensitive to nuclear reaction rates measured in laboratories, and those measurements carry error bars large enough to shift predictions by significant margins. Remember the nuclear reaction calibration that anchored an entire generation of predictions? When fresh accelerator data arrived, the measured value jumped by a margin exceeding the old error bar. That recalibration dragged the theoretical boundary of the forbidden zone by dozens of solar masses. The implication is clear. Every published prediction about which stars form black holes and which stars are completely destroyed carries an invisible asterisk. The prediction depends on a number that the labs have not settled on. Until that number is pinned down with smaller error bars, the predictions remain conditional. We do not know how long simulations need to run before the answer stabilizes. The Burrows group showed something striking. Extending one calculation from a handful of seconds to nearly 4 days of stellar time transformed the final product entirely. What looked like a stable compressed remnant turned into a gravitational trap buried by returning debris. Most published simulations across the field stop at roughly 1 second. Nobody knows how many of those results would change if extended to comparable timescales. The computational cost of extending a single run is prohibitive. Research groups operating under pressure to publish make the practical choice. They stop at the point where the dramatic physics appears finished. And we know that choice can be wrong. We do not know whether the Vera Rubin Observatory will find anything. The observatory represents the most powerful survey instrument ever built for detecting faint, slow transients. An 8.4-meter mirror, photographing the entire southern sky every 3 nights, operating for a decade, starting in the mid-2020s. If faint supernovae are as bright as the models predict, Rubin should detect 1 to 4 events per year. Should 10 years of Rubin data accumulate without a single detection, the field faces a fork with no comfortable path. One branch says the models overestimate how often massive stars collapse quietly, meaning the entire theoretical framework needs rebuilding. The other branch says the collapses happen constantly, but the optical trace is so feeble that no mirror on Earth can resolve the signal. One branch rewrites the physics. The other branch means the evidence sits permanently out of reach. And we cannot predict which fate awaits a given star, not roughly, not reliably. The outcome depends on the exact structure of the stellar core, measured at the moment of collapse, which depends on millions of years of nuclear evolution, which depends on reaction rates measured in accelerators with large uncertainties, feeding into computer codes that handle turbulence and mixing differently depending on which research group wrote the software. Schneider and colleagues mapped the full range of massive star endpoints and found not a clean function but a cloud, a spray of final states so disordered that 2 neighboring stars on the mass ladder could face entirely opposite fates. The field has not yet achieved predictive power for individual stellar deaths, and achieving that power may require constraints that do not currently exist. That is the balanced verdict. Proven, the explosion mechanism requires three-dimensional chaos and turbulence. Proven, some mass ranges collapse without visible explosions in the models. Possible, a significant fraction of the most massive stars end in silent collapses. Unknown, the exact boundary between explosion and silence. Still unresolved whether any purely silent collapse has ever been observed. And hanging over the entire question, whether a decade of searching will change the count from zero. The mystery survives scrutiny. The silence is real. But the honest answer is that silence may not mean what we assumed. But here is the part that reframes this entire investigation. Because the balanced verdict is honest, and the balanced verdict is accurate, and the balanced verdict is also incomplete, one more piece remains. A piece that nobody in the popular conversation about stellar death has reckoned with, and the piece does not support any side of the debate cleanly. The piece destroys the premise. We built this case around a binary. Stars either explode or vanish, spectacle or silence, light or darkness. The entire investigation rested on the assumption that those two categories exhaust the possibilities. And the physics says otherwise. The physics says that every single formation event, without exception, passes through a third state. A state that lasts only moments. A state that nobody on the outside would see with a conventional telescope, but a state that is, by definition, neither spectacle nor silence. A state that leaks. Here is why. When the iron core of a massive star gives way, the inner material compresses past nuclear density and rebounds. That bounce creates a transient compressed object, a temporary structure, and for a window measured in fractions of a second, perhaps a few seconds, the structure behaves exactly like what astronomers would recognize as a neutron star, emitting particles, generating ripples in the fabric of space, existing, briefly, as a genuine detectable astrophysical object. The structure cannot know what is coming next. Infalling debris from the surrounding envelope has not yet arrived. The signal from the approaching crush travels at the speed of sound through ultra-dense matter, and the signal is slower than the light-speed particles already streaming outward. The compressed object radiates a flood of neutrinos carrying an energy budget equivalent to annihilating a significant fraction of the mass of our Sun. And those escaping particles interact weakly with the outer envelope. That interaction matters. The flood of escaping particles nudges the outermost hydrogen layers off the dying star. Not violently, not spectacularly. A gentle mass shedding that produces a dim optical signature, a reddish glow persisting for weeks. Fainter than any catalogued supernova by orders of magnitude. Invisible to every survey that has operated so far. But physically real. Mandatory. Unavoidable. According to every three-dimensional simulation that tracks the full particle transport. And then the temporary structure is overwhelmed. Returning debris accumulates once the mass crosses the threshold where no known force can hold the object together. The compressed core drops behind a boundary from which no signal returns. Abruptly, the particle stream terminates. A detector like Super Kamiokande, watching a nearby galaxy at the right moment, would register a sharp burst of particles, followed by sudden silence. A gravitational wave detector would measure a changing signal that shifts character at the instant of final collapse. The footprint is brief. The footprint is faint. But the footprint is there. What does that mean for the picture we assembled? Every thread in this investigation assumed a clean binary. Explosion or nothing, the transient phase demolishes that binary. No, nothing exists. Every collapse event broadcasts a signal before the final curtain drops. The stalled mechanism we uncovered at the start of this investigation, even when the blast front fails completely, the particle flood still fires. The missing giants that vanished without a trace. Not missing. Whispering. Radiating a glow too dim for any survey that has searched so far. The wrong answer we found when the celebrated result turned out to be a disguised formation event. That disguise works because the flash overwhelms the faint signature underneath, and the cliff edge between total destruction and total silence. Even at the bottom of the cliff, a faint glow persists on both sides of the boundary, and the barren search across 231 galaxies. The instruments were calibrated for a brightness floor. If the actual floor sits lower, every negative result reflects a sensitivity problem, not an absence of events. The purely silent death, the centerpiece of the mystery we chased across this entire investigation, may not be physically permitted. Absolute silence requires that zero energy escapes the collapsing system, and the particle physics forbids that condition. Neutrino emission is mandatory. Gravitational wave radiation is mandatory. A faint optical trace, while not guaranteed, follows from the energy budget with high probability. The silence everyone feared is not silence. The silence is a signal below the noise floor of every instrument that has listened. Physics demands they occur. What remains open is not existence, but detectability, whether human engineering can construct an instrument sensitive enough to register the faint signal that accompanies every crossing of the final threshold, and so the file does not close. The case transforms. The next generation of observatories, particle detectors, and gravitational wave networks operating in concert may finally resolve the whisper that optical instruments never had the sensitivity to catch. Or the whisper may prove even dimmer than the models anticipate, and the count will remain at zero for another decade. Either way, the question that drives the next era of stellar astrophysics is no longer the question we started with. We started by asking whether the universe erases the most massive events without leaving evidence. No. Evidence is always left behind. What will occupy a generation of astronomers is a different question entirely. Whether human beings can build an instrument precise enough to hear what the cosmos has been whispering all along. Somewhere tonight, a massive star sits alone in the dark. The core is giving out. No telescope is pointed at the right patch of sky. No alarm will sound. The star will dim slowly over weeks, a faint red glow fading below every detection threshold. And then nothing at all. The sky where the star used to be, empty and silent, whispering to no one. The fascinating part is not that we have answered the question about black hole formation from stellar death. The fascinating part is that the evidence keeps pointing us toward a reality bigger and stranger than we expected. Science is not about having all the answers. Science is about asking better questions every time we think we have figured the cosmos out. I hope you found some value in this deep dive. If you did, and you want to support the research and the late nights that go into these videos, hitting that like and subscribe buttons really helps me out. Your support makes a huge difference and allows me to keep digging deeper into these mysteries that the universe keeps handing us. But mostly, I want to know what you think. Did I miss anything about how black holes form from dying stars? Did any part of this surprise you? Let me know in the comments. I will catch you in the next one. Let curiosity guide you. Keep learning, and know that you are always appreciated.